Hello and welcome. My name is Chris Eberl. I'm a senior solutions architect, and today I would like to talk to you a little bit about Headless Playback. So what is Headless Playback specifically? It refers to media playback that runs without a visible user interface, often in the background or off screen. It enables running your video playback on a different JavaScript thread, and that is most important for most apps who want to play video right away in the background. Related concepts that you might be familiar with are either headless browsers, like Puppeteer, Playwright, that run without a graphical UI, which are useful for automated testing or rendering, or service workers, like background scripts in browsers, that run independently of UI, enabling offline support, push notifications, or caching. So why bother implementing headless playback anyway? It is actually pretty important for complex TV apps because data parsing of the media playback and the UI interaction can or will run on the same JavaScript thread otherwise. This can cause performance conflicts or contention, especially when you play, pause, seek, or trying to browse your library while watching content. There's two types that are not mutually exclusive. Usually the media playback is affecting the UI responsiveness, or the UI is affecting the media playback. We see when you implement headless playback, it usually improves your time to first video frame by 30% or more. This heavily depends, is your app an app that uses video playback right away? Then you will see bigger gains, versus if you browse through your library first or let the user browse through your library first, then you might be more in the up to 30% range. Before we dive in further into the implementation, I do want to take a step back and I do want to talk through how does my video stream actually land on my TV. For that, I'm taking a quick example where we say in a European city, we are doing some live sports event. The live event is being shot with a camera equipment somewhere in Europe, and number two, the video is being transmitted into local broadcast center or truck. Number three would be the video feed is then delivered via transatlantic fiber, sometimes satellite as a backup, into a node on the East Coast on the USA so I can watch it from my home in Los Angeles. The format is usually there still like 2110 or SDI. Number four would be video lands at the broadcasting facility and its production control rooms in the AWS cloud. Number five, video feeds and renditions are being produced in playout and transmission. And number six, the sport event lands on your streaming app on Fire TV for you to consume. We mentioned playout and renditions, and this is what's important and marks the case why Headless.js is so important to be implemented on our devices. Do you see the first red box on the left side where it says 720p.m308? That is called an HLS manifest. In this example, we're using HLS as the showcase, but similar things apply to MPEG- or other formats. If we look at the orange box, which is the file 720p.m308, we actually have an entry that is called xinf 6.000. This identifies chunks of 6 seconds. These are actual network requests. So every 6 seconds, I'm looking for more data to come into my video player in form of segment 1.ts or segment 2.ts. This can cause a significant network overhead depending how large your chunk size is. For example, if this is 2 seconds or even out of spec, which would be lower than 2 seconds, then you would have some real trouble getting your device into a performance state where it can handle UI and playback at the same time. Hence why we advise going the Headless.js route right away so you're not under any of these constraints. Jumping in more conceptually, what that means for your media player. So for example, media players like Tracker Player, HLS.js, Dash, Bitmovin, or how they all are called, perform CPU-intensive tasks in JavaScript like parsing an HLS media manifest and fetching these TS segments, which can impact UI responsiveness and fluidity of your application. This impact is particularly noticeable during live TV playback with large DVR windows that also creates large manifest sizes or already has large manifest sizes. Jumping ahead in the implementation conceptually, you essentially need to achieve 3 tasks to offload playback to a background service. 1, you have to create a server in your service component. 2, you got to create and start the service from the app. And 3, refactor the client in the interactive component. Luckily, a lot of that is handled already by the framework that we provide you as part of the SDK. So you just have to follow the integration guide that we already have published as part of our public documentation. I do want to highlight a couple of implementation in form of like sneak peeks. So the rough outline, number one will guide you through the manifest toml changes. They are very straightforward. Number two, you add to your service.js that already exists as part of your project. This is where you actually implement the onStart and onStop service. Number three then would be you create the headless service file. Number four is where the rubber hits the road because you gotta adjust your player code. And I specifically want to point out number A here is that you initialize your client once in the app.tsx, which means you eat the initial cost once at app start and then never again. In addition, as you already do, and as part of how to put your app properly into background mode, as it is also part of our documentation, you will also need to get rid of the player there properly as part of that process to not cause any malfunction or weirdness the way how your app functions. Thank you for your time today, and as always, happy coding.